Have you ever tried solving the Rubik's Cube? If you don't cheat by sticking the sides yourself, it's not that easy, right? Okay, what exactly do you do to solve it? Well, you rotate one side at a time until you get the result you want, right? Essentially, you can only rotate one of the 6 sides clockwise or counterclockwise. The Rubik's Cube actually forms a mathematical group. Okay, but what is a group anyway? Well, a group is a set of elements, along with an operation that combines them. The elements of the group represented by the Rubik's Cube are the possible rotations you can perform, and the operation is the combination of these rotations. Let's say these capital letters represent the rotation of a side by 90 degrees clockwise, and the corresponding lowercase letter represents the rotation of that side counterclockwise. These are elements of my group, but so are all possible combinations of these rotations. However, different combinations that lead to the same result are counted as a single element. For example, I don't need to include this element in the set, because rotating this side 5 times clockwise is equivalent to rotating it once. Now that I check it again, I can also remove this element, since it's already represented by another element. Can you spot the other element? By the way, there are these many unique configurations, which correspond to the number of elements in this set. Crazy, right? Okay, to be honest, a set with an operation must fulfill some basic properties in order to be called a group. Closed under operation. If you combine 2 rotations, for example, you rotate the bottom side and then the back side, you get a new cube configuration, which is also an element of the set. Speaking more generally, for any elements x and y, if x and y are elements of G, then their combination is also an element of G. Identity. There is an element in this set, usually denoted by a small e, which leaves any other element unchanged when combined with it. I'll place this right at the front of my example set and highlight it to emphasize that every group contains an identity element. In the cube example, E represents no rotation. So if I rotate a side to the left and then stop, it's the same as not rotating it first and then rotating it to the left. Eventually, I've only rotated it to the left once. Inverses. Every rotation can be undone with an inverse rotation. For example, if I rotate the front side 90 degrees clockwise, the inverse rotation 90 degrees counterclockwise reverses the action. Typically, the inverse element is written as to the power of -1. And it's somewhat obvious that when these 2 elements are combined, the result must be the identity element. So this element is the same as E and also doesn't need to be listed twice in the set. Thus, in a group, there is an inverse element x to the power of -1 for all x, so that their combination results in the identity element. And the last property a group must satisfy is associativity. In general, that means that for 3 rotations, x, y and z, it doesn't matter whether you combine x with y first and then combine the result with z, or combine y with z first and then with x. The result remains the same. A group is, therefore, something very general. It consists of a set of elements and an operation of these elements, as long as these conditions are met. By the way, if a set G with an operation forms a group, it's often written as a tuple like this. Since an operation can be any arbitrary abstract action, it's often represented by an asterisk, or sometimes by other symbols like bullets or circles. Let's now look at an example with numbers, specifically the set of integers. As you know, these can be added and subtracted. But since subtraction is just addition with a negative number, we will only consider addition as the operation for this group and write a plus instead of an asterisk. It's fairly easy to see that the previously mentioned group axioms hold for the integers with the addition operation. When you add two integers, you always get another integer. So the integers are closed under addition. Apparently, the identity element is 0, since adding 0 to any integer gives the same integer, no matter whether the 0 comes first or second. Furthermore, for every number there is an inverse, or more precisely, an additive inverse. For example, -5 is the additive inverse of 5, and their sum gives the identity element 0. Associativity is also satisfied, as it doesn't matter where we place the parentheses, the result is always the same. So the integers with the addition operation form a group. Additionally, in this case, the order in which I add the numbers doesn't matter. When this additional property x plus y equals y plus x holds, the group is called commutative group or Abelian group, named after the mathematician Niels Henrik Abel. It's not always the case that a group is commutative. The Rubik's cube group, for example, is not, as the order of the rotations cannot simply be swapped. So, while the integers form a group under addition, they do not under multiplication. Since any integer other than 1 or -1 does not have an inverse element. For example, 5 must be multiplied by this fraction to get 1, which is the identity element for multiplication. But fractions are not integers. The set of rational numbers with the multiplicative operation, however, forms an Abelian group. Right, and in the multiplication group, we always exclude 0, since 0 can never have a multiplicative inverse. 0 multiplied by anything can never equal 1, you know? Well, I didn't mention the additive and multiplicative groups for nothing. These groups form the foundation for defining mathematical fields, which are necessary to define vector spaces. And that's where math starts to get really cool.